Hello students, welcome to lecture of Kinematics and Theory of Machine. Myself Professor Patel, and we are going to continue our chapter Gear, and topic we will cover in particular this lecture is a length of path of contact, which is very important because all the numericals from this chapter Gear depend on this theory, and formula we will derive in today's lecture will be used in all examples. Okay, let's start. Okay, let's start length of path of contact, which is very important theory from Gear, and all numericals of this chapter will be depend on this theory. So first of all, we understand what is the length of path of contact. So you can see here the point of engagement, and at this point two teeth are in a come to engage, and they are transmitting the motion up to this point. After that they will disengage. So we have to find this length, which is known as a length of path of contact. Okay, you can see this is the point and it is transmitting motion, and this is disengaging. After that gear will be go down. So this point you can see here. What is this point? This is the point at which means addendum. This is the addendum of driver and dedendum of driven. So you can see three circle here, and this is the total derivation. So this is we are going to derive, and we are using total geometrical relation of a gear, addendum circle, pitch circle, and all that. So pay attention, we are going to derive this step by step. Before that I am going to show you these circles. You can see here three circles. This is the circle, addendum circle. After that at the center it is a pitch circle, and bottom of the means smaller circle is a base circle. And same as the three circle you can see from the top also. This is the base circle of the driven gear, this is a pitch circle, and at the bottom this is a addendum circle. And to pitch circle at a contact point we know that it is a pitch point. Okay, so all these three circles you can see here, base circle, pitch circle, and addendum circle for the both gear. So let's start. Okay, let's start step by step. So let's take two gears with a center as a O1 and O2. This is the gear number 1, and second is a gear number 2. You can see the three circles like this. This is the base circle, pitch circle, addendum circle, and same as from the opposite gear. This is the base circle, center as a pitch circle, and maximum diameter will be the addendum circle. Okay, so the point of contacts you can see here. First is a K is a point of engagement, and L is a point of disengagement, and P is a pitch point at a point of two pitch circle. Okay, this is the 3 points, and we are trying to draw the line because it is the normal at a point of contact. Also we have drawn the MN in our last theory, same as this. It is also known as the MN also. So what we are going to do, we will do normal on this normal. Okay, so we have drawn these normals like O2N and O1M on a MN. So now it is known as a normal MN. Then I have identified these circles. You can see this dotted line is the pitch circle of gear 2, and the outer circle is the addendum circle for the gear 2. Okay, same two circle you can see from the bottom. In gear number 1, smallest circle is a R, small same two circle you can identify from the gear 1. Dotted circle, blue dotted, is a pitch circle, and largest circle is a addendum circle. Okay, small RA and R, capital RA and R. Okay, so we are going to contact this K point because this is an addendum point, on an addendum circle of gear O2. So we have connected this O2 to K, and same as connected O1 to N. Okay, so for next, what we are going to, you can see the angle between the O2N and O2P will be phi, and same as O1P and O1M will be the angle phi, which is also known as a pressure angle. So phi. Okay, so let's start the identify all the geometrical relation we have derived this point up to this point. So first of all, you can see here O1L, you can see it is a addendum radius of the gear 1, so small RA. Same as you can see here, this is the O2K. O2K is a addendum radius of gear 2, capital RA, O2K. Same as you can see O1P. O1P is a pitch circle radius of gear 1, and O2P, which is a pitch radius. You can see here it is the pitch radius. Okay, so up to this point, this is the 4 relation you have derived, and after that you can also see that here you check this triangle O2PN. In that, you know the O2P is a small r, O2P is a capital R here, O2P is a capital R, and angle is a phi. So what will be this component? This component will be R cos phi. And same as you will use this relation also, PN will be capital R sin phi. Okay, so that's how capital R means pitch circle has a 2 component, 1 and 2, R cos phi and R sin phi. So O2N will be capital R cos phi, and same as O1M will be small r cos phi. Okay, I will show you like from this O1PM triangle, and you know that this is the small r and angle is a phi, then it will be R cos phi, and here MP, which we'll use in our next steps, R sin phi. Okay, remember that small r sin phi is MP. Okay, till point. So next we are going to derive some relation. What we want to measure from all this, we want to measure this KL. I repeat again, we want to measure this KL, and how we will going to find this? We will divide this KL into 2 parts. Okay, from the pitch point we will first find the KP, and in second portion we will find the PL, and that's how we will find total KL. Okay, there is no possibility of finding directly KL, so we will find KP and PL individually. So you can see from the triangle, which triangle? O2KN, O2KN. So from this we will find KN, totally KN, and after that we will find, you already know the PN, so what we will do, KN minus PN. So we have this, we will find this distance, we will find this distance from K to P by this. Okay, so KN minus PN, we will going to do that. So first of all, from this triangle O2KN, what will be the KN? As per Pythagoras, you already know that under root O2K square minus O2N square, and among this you have to find this O2K and O2N. You know that already, O2K and O2N. O2K, here check this, O2K is equal to capital RA, you already know that, and O2N O2n is equal to, already you know, the r cos phi. So that's how you will put these values in relation, capital R square minus r square cos square phi, and then you will find this Pn. Pn is a sine component of capital R sine phi. So we want to find this distance Pn, and what will be the Pn? Pn is equal to total Kn minus Pn. So we will find the Kp. Okay, so path of approach will be Kp is equal to Kn minus Pn. This path of approach means there is a total length of path is divided in two parts, and from engagement to center point means pitch point, it is known as a path of approach. And after pitch point we are going to disengage, starting of disengage up to L point. So this is that PL is known as a path of recess. So total length of path is divided in two parts, path of approach plus path of recess. So you already know that what is the Kn. We have already derived this Kn. And what is Pn? It is r sine phi. Okay, so we have derived this length of path of approach. Okay, this is the approach, and same way we are going to derive the recess. Okay, so length of path of contact is now we are going to start the path of recess by same relation. Now we are going to consider which circle from the bottom. We are going to consider this rectangle. Okay, this rectangle, and same manner we will repeat for finding what we want to find. I am showing you, we want to find this PL. And how we will find this? First of all, we find total ML, and after that we will minus this MP. This MP we will minus from that. So we will find the PL. Okay. So ML is equal to O1L square minus O1M square. ML is equal to ML is equal to RA square minus R square cos square phi, and MP is equal to R sine phi, sine component. Okay. And same relation you will find, same relation as a length of path of approach, only change is there. This is all the small r's. You know that small r because for gear number 2 we have taken. Okay, so small r, same equation PL. So now the total length of path of contact we are going to derive total length of path of contact, which is equal to Kp plus PL, Kp A to P and plus PL. Okay, so it will be like this: Kp is equal to under root capital R square minus R square cos square phi R sine phi, and PL is equal to same way. Okay, so total will be but whenever you this equation use in an example, don't put this together. We will always find the Kp and PL individually. Why? I am giving you an example. If you find the Kp is equal to around 20, the PL will be also be around 20, maybe 18 or 21. Okay, so you can verify the answer with Kp and PL. And if you put all these in one equation, you can't verify your answer. Okay, so this is the length of path of contact. Now we are going to our next theory, which is known as the length of arc of contact. So right now we have measured length of path of contact, means point of contact, means from K to L, but this distance we want to measure along the pitch circle, in curvature way. So how can we measure that? So first of all, we have to this projection from K to pitch point, pitch circle on, and same as a KL2 on pitch circle. and that's how we will measure. After that we will measure from this point to this point, and this is the arc. So there is a GPH. This is the point G. P is a pitch point at a center and H is at an end. So this total arc is a combination of two arcs, same as a length of path. G to P, G to P up to this point, which is known as a arc of approach, and after that P to H, which is known as a arc of recess. So same way we will find this. So we have the relation for the arc of approach is equal to length of path of approach divided by cos phi, and same as the length of arc of recess, which is the PL upon the cos phi. And okay, total arc of approach, which will same as a KP upon cos phi plus PL upon cos phi. And if you have the KL, if you have the length of path of contact total, so it can be divided by cos phi and you can find the length of arc of contact. Okay, so it is very useful relation we will use in a numericals. Okay, so now next we are going to know the what is a contact ratio or number of pair in a contact. Okay, so first of all I am giving you simple example, like if you imagine two gears are there and very small teeth on both gear, so number of teeth in a contact will be high. Okay, so there, that is we are going to count or learn the number of pair in a contact, which is also known as a contact ratio. So what is a contact ratio? Number of pair of teeth in a contact is defined as a, it is a ratio is the length of arc of contact divided by PC. Okay, circular pitch pi m, okay, also known as a pi d by t, and in between them m is a module. So contact ratio is equal to length of arc of contact divided by PC. If the answer is 1.6 for the contact ratio, it doesn't mean that there is a 1.6 pair of teeth in a contact. Means there will be one teeth will be totally in a contact, one pair of teeth, and second will be also in a contact throughout the motion. That is its meaning of 1.6. And if the contact ratio is a less than 1, what is the meaning of less than 1? Means there is a possibility of there is a no contact between the two teeth of a gear. So there will be always contact ratio must be more than 1. Okay, for continuous action always contact ratio is higher than 1. Okay, and larger the contact ratio, more quietly the gear will be. So there is also we have to find this angle turn by the pinion and gear wheel when one pair in a contact. So we have to find the angle turn by the pinion. Means if two teeth are coming in a contact, what angle they make up to the disengagement point. So let's learn. I'm giving you one example. This is the pitch circle. Okay, this is the center of this gear, and point, this is the point of contact, means engagement, and up to this point they are in contact, and at this point they will disengage. So what is the angle made by the pinion? We have to find this angle. So it is very easy how you can find this angle. So first of all you have to find the length of arc, okay, which is you already know that, and total circumference of pinion, okay, and 360. So very simple logic behind this equation. Same as for the wheel, length of arc of contact into 360 divided by the circumference of the gear. Okay, so also these points we will discuss in some numericals. Velocity of sliding point at a point of engagement, point of disengagement, and sometimes also maximum velocity asked. So check this. First of all, the angular speed of the pinion, which is known as omega, angular speed of the wheel, which is known as omega 2. Pitch line velocity. What is pitch line velocity? Pitch line velocity means if two circles are there and I am say there is a point, pitch point we can say here, and its velocity is in this direction, what will be the velocity with respect to this point? With respect to this point, what will be the velocity? According to gear 1, velocity will be omega 1 into small r, but if I am considering with respect to gear 2, velocity will be omega 2 into capital R. So point is at a between, and this is a normal common point between two gears. So according to both gear will be velocity, we can find the velocity omega 1 into small r or omega 2 into capital R. And second is the gear ratio, omega 1 upon omega 2 is equal to capital T by small t. It is a gear ratio. And then sliding velocity at a point of engagement, which is omega 1 plus omega 2 into kp, and sliding point of disengagement, which is known as omega 1 plus omega 2 into pl. This is the sliding velocity at a L point, and sk means sliding velocity at a k point, which is the engagement point. So kp and pl, but sometimes they ask the maximum velocity of sliding, vs, and it can be find out. You can find both individually. You find this, and after that you can select the maximum, or you can directly derive this, because kp and pl is a difference in these two equations. So you have to find that what is the maximum value of kp and pl, and among them you can use any one for finding the maximum. Okay, so we have to find the which is the maximum value among the kp and pl. So that's it. This is the all the formula list for the gear, and in